Welcome back to the video lectures of mechanical vibrations. In the last video lectures we have derived the equation for the free damped vibrations. That's we are going to be say the characteristics equation. From that we have identified or we determined the displacement of the vibrating system. By the one assumption is that the dissipation of energy is taking in the exponential way. The vibrations of the motion is going to be dying out in the exponential way. So on that basis we derived that equation. In this video lectures we will see that's going to be a critical damping constant. What's the critical damping constant here? As you see that, so in this equation, that is the damping force is equal to C into velocity. In this case this is called a damping coefficient. Then what is this critical damping a constant or critical damping coefficient? So when this parameter will going to be critical damping coefficient, that's we are going to be checking here. So from the roots lambda 1 comma 2 that is equal to minus c by 2m plus or minus square root of c by 2m whole square minus k by n. And this part we are going to be called the radical. This will going to be deciding whether the system is going to be over damping or critical damping or under damping. So then what will happen? I have taken separately that c by 2m whole square minus k by m is equal to 0. Then this condition it will become, that's going to be the damping coefficient will become the critical damping coefficient. So then I am going to be replacing that cc by 2m, that's going to be, so this 2 is going to be towards the right side of the equation, that will become the square root of k by m. So that's is equal to omega n. As we know that the cc is equal to 2 into mass into natural frequency of that system, we are going to be say the that is going to be critical damping coefficient. I hope you understand what is the critical damping coefficient. This is going to be the damping coefficient will convert it into critical damping coefficients when these radicals are going to be equal to 0. So on that basis we write that the damping coefficient, critical damping coefficient is equal to 2 into mass into natural frequency of that system. We have seen that the critical damping constant or critical damping coefficients we have derived from that equation. In little further we are taking that the damping ratio. The damping ratio here that's representing with the epsilon. So what is the damping ratio? As we know that we do have derived C is going to be the damping coefficient and Cc is going to be the critical damping coefficient of the damped vibration system. So then what will happen? I am going to be taking the ratio of these two. That is the ratio of the damping coefficient to the critical damping coefficient of that vibrating damped system is called damping ratio. So that's I am going to be show mathematically that epsilon is equal to damping coefficient by critical damping coefficient. So from this equation, we are going to be simplifying the radical of that equation. That's going to be Cc is equal to that the critical damping coefficient as we have seen in the previously. That's going to be 2 into m into omega n, right? That's going to be mass into and natural frequency of that system. So then what happened? I'm going to be taking the radical from that equation. So we do have that equation that's going to be c by 2m whole square minus k by m, that's equal to 0. So I am going to be modifying this equation here. So that's going to be c by 2m, that is equal to, I am going to be multiplying and divided by with the critical damping coefficient. So then that's c by cc into cc by 2m. So then what happens? Cc is going to be cancelled, there is no effect of our parameter over here. So then as we know that c by cc is going to be, it is going to be epsilon, and c by cc 2m is going to be from this one cc by 2m is equal to omega n, right? And by simplifying this parameter and these parameters we got the epsilon that's into natural frequency of the system. Then finally I'm going to be substituting in the amplitude equation, that is going to be x value, and I'm going to be modify that part. So we have derived that damping coefficient, damping ratio and the critical damping coefficient and the c by 2m, the radical parameters, that's we converted into epsilon into omega n. These values I am going to be substituting in our amplitudes of the vibration. That means the motion of the vibrations is going to be. That's we have witnessed this equation. That's going to be x is equal to a1 and a2. These are the two amplitudes we are getting, and then we substituted in this equation. That's going to be x is equal to a1 e to the power of lambda 1t plus a2 e to the power of lambda 2t. So from this equation we derived already in that in the last video lecture, and then I have substituted C by 2m is equal to epsilon omega n. So then if once I am going to be substituted in this equation, we are going to be getting this level of equation. I hope it is visible to you all that x is equal to. Once I am going to be taking in this position omega n, that's going to be natural frequency, I am going to be keeping outside that root. So then what the final equations we are going to be getting here, the x is equal to a1 e to the power of minus epsilon plus square root of epsilon square minus 1 omega nt plus a2 e to the power of minus epsilon minus square root of epsilon square minus 1 omega nt. This is going to be amplitudes of the vibration. This is going to be the displacement of the vibrations when we are going to be converted into, that's going to be damping ratio and critical damping, and the radical, that's we change it to in this way. This way we are going to be solve the coming equations, and we are going to be characterizing the vibrations of the system. Thank you.